Okay, before I start, how many people have had surgery here? All right, how many folks had a family member or have cancer themselves? Okay, so you may understand now a little bit of what I'm going to talk. I'm a regular anesthesiologist at a major cancer center, and we have several problems with our cancer patients coming to the operating room. When a patient comes to the operating room, everybody goes to sleep, but when it goes, there is a period where they are sleeping, that a lot of things happen to your body because of surgery and because of anesthetics. So I'm working at MD Anderson. I have an affiliation in the Data Science Oncology group, and here is the mastermind of this work, Dr. Switzerland, and our work is being partially funded by MD Anderson. So, as I said, 50% of the patients with cancer at some point will need surgery, either a major surgery or a minor surgery. It doesn't matter. You may need to go to sleep. What happens is when you are asleep, we monitor your vitals. People have seen probably on TV that anesthesiologists are sitting on a chair. Dr. Glokofen makes joke about us, and they said, okay, what is going to happen when the patient is asleep? One thing that happens all the time is the patient gets low blood pressure. Low blood pressure, if it's a couple of minutes, it's not a big deal. But if it's more than a couple of minutes, 5 minutes or beyond, has serious implications on your health. First, you may develop acute kidney injury, so the kidney gets sad. Second, the heart doesn't like it, and the heart is not going to have a heart attack, but it's going to get injured. That injury to the heart or the kidney is a predictor of mortality within 10 years, even if you survive your cancer. So intraoperative hypotension is pretty bad. So what happened is, can we predict hypotension? Do we know how to do it? Well, there are models that have been built for at least 10 years. These models are okay, but randomized controlled trials have consistently failed in showing that predicting and treating these patients improve outcomes. And that is a very big issue because we don't know if the models are not the proper models or we don't know how to treat. So we decided to start looking at, can we do better than those models? And some of these models are commercially available. Our work is within MD Anderson, and we have already filed a patent for this. What we did is the following. We took patients who have liver surgery. Liver surgery is a major surgery. The surgeons will take a piece of a tumor or a piece of a liver when patients are going to surgery. And at some point on that surgery, around 60 to 80% of the patients will get an episode of hypotension. So what we did is we look at 10 minutes of data where we have all what we call physiological data. Physiological data meaning is we know your depth of sleep. We know your blood pressure, systolic blood pressure, diastolic blood pressure, and the mean arterial pressure. The mean arterial pressure is important because that's how we define hypotension if it's below 65 millimeters of mercury. But we have respiratory variables. We know how much anesthetic we were using. And on top of that, we put 3 key variables: age, sex, and BMI. And ASA, which is a measure of comorbidities or comorbidity burden. So when we look at mean arterial pressure only, this is the AUC that we have. This is what other machine learning algorithms have shown. They do not predict better than just having your mean arterial pressure. And that this is a problem. This is not optimum at all. So what we have done, and I don't want to take all the credit, this is work by physicists and machine learning folks in our group. We developed what is called a multi-dimensionally, multi-model voting strategy. This is based on an ensemble of random forests, and basically what we said is we took 11 random forests, and we asked, can looking at this predict better than NAUC and we took 10 minutes, and then we started sliding, and then we ask every time that you are going to see or predict an episode of hypotension, we're going to call a vote that we have 11 of these forests. And what we found is that we did much better than AUC at around 0.95. With that in mind, and we published this. This is the first time that we are using an algorithm that does not require contour of the blood pressure. It's just the number of the blood pressure, which is different from what is available as of now, at least commercially. But we have some challenge. The challenge that we had, first of all, we took only liver surgeries. Liver surgeries are known to be, or patients undergoing liver surgery are known to have multiple episodes of hypotension. So we needed to expand this. Now, we asked anesthesiologists, what do you prefer? And 2 or 3 anesthesiologists said, well, I want this and I want that, because if I have this, I can predict better than this. So first challenge is how we're going to make it user-friendly. And second, we have more important issues. Not that anesthesiologists are not important, but there are multiple types of surgeries. Even within a liver resection or liver surgery, surgeons can do it open or can do it laparoscopically or robotically, what we call minimally invasive surgery. Surgical position changes even within the same type of surgery. Extreme head up or extreme head down occur when you are during surgery, and sometimes when we do, let's say, renal surgeries, patients are on lateral, they are not on supine. When we do spine surgeries, patients are face down. And then we have another issues. Are not patients with cancer, if you have gotten prior therapies, are not exactly the same. We know that chemotherapies will impair your autonomic system, for instance, so the mechanism leading to hypotension may be different. And last, the duration of surgery is important. 30 minutes of surgery, patients typically getting a biopsy. Healthy patients, 1 episode of hypotension may not have a serious implications in your health. But a surgery might last 12 hours, like in a spine surgery, and you have multiple episodes of hypotension. That period of time may add up to 1 hour cumulative of hypotension. And we know that that is not good for your health. So what approach we start taking? First of all, we start doing sort of an internal validation by looking at, by adding MIS liver resections, minimally invasive, colorectal surgeries, open and minimally invasive, and we did nephrectomies, also robotic or open nephrectomies. And since we know as a physicians that these procedures are radically different, we first of all said, we have within the same type of surgery 2 classes, open versus MIA. And that's one of the things that we were interested in. Can we predict within a class, within all MIAs or within all open surgeries? Or we can create a supermodel. A supermodel is that we have all types of surgeries, and we said, this is probably what an anesthesiology would love to have, a monitor that can predict regardless of type of surgery. So here we have the initial 6 types of surgeries. We have open liver lobectomies. Lobectomy means that we took part of your liver. Open colorectal surgery, open nephrectomies. These are the numbers of patients. And we have MIS cases here. And we call it A, B, C, D. And these are the classes for opens. And they are the classes for minimally invasive. We call classes. We don't know if this is the right way to classify them, but we call them classes. And then we created this supermodel. In all cases, we use 50% positive IOH and patients with 50% negative IOH. We use this training validation strategy, and we held filled out 100 cases positive and 50 positive and 50 negatives. We created this matrix, and I'll show you, you have an idea of what it is, to see what happened when they are perfectly matched in distribution, when they're fully within distribution, partially or out of distribution for each type of surgery, for class, and for our supermodel. So, first of all, we look at the model A. Model A, remember, is our initial publication. This is our initial paper. And we look at what happened with the matched distribution. It's very, very good performance. When we went out of the distribution, still pretty good. It dropped, you know, as you move into different surgeries. But when trying A to predict and test partially within the distribution, we performed really well at around 0.87. And then we use A to see what happened within the supermodel, which is partially within the distribution. And it dropped the performance as expected, but we did really well. And as in our original paper, we know that the number of votes that we need as a threshold for the prediction, remember we asked 11 random forests to tell us how, or to say, okay, if we have 6 or more, we have an episode of hypotension, and it remains the same here. Then we said, okay, we are going to take this class to predict A. This is fully within distribution, and you can see when we are fully within distribution, if you use a class to predict a particular surgery, we do really well. When we are out of distribution, we drop again around 0.85 or so, if you look. But when we have matched distribution, here we go back up again. More importantly, when we use the class to predict all the surgeries in the supermodel, it performed really well. Here, the sweet spot, as I like to call it, for the number of votes is around 8, 7 to 8. And this is the supermodel. In the supermodel, we trained the 3 open surgeries, the 3 minimally invasive surgery. If you are partially within the distribution, we perform really well. Then for each class, you drop, for each procedure, you started dropping. When we are back into our class, we go back to 0.85%, and when you have matched distribution, we go by 0.85 or so percent. And this is the metrics, another way to see that. These, again, are the matched distribution. We do really, really well. And you can see what happened when it is within partially within the distribution and full distribution. Now, what we found? Well, this is the first time that we are testing our MMB model outside open liver surgeries. And this is important. We could have taken a different route and put every single operation that happens at MD Anderson. But we took, I would say, a more cautious approach to learn what happened, not only within the same surgery, but within classes and then the supermodel. As I said, the highest performance is within distribution. We have a small drop in the when we have outside the distribution, but 93 or 88% is a little better that, or I would say yes, a little better than what is commercially available. Commercially available for the prediction within 5, 10, and 15 minutes is around 82% or so, 83% when you are closer to 5 minutes. Now, we created this class, or we identified this class models, the open versus MIS, and the performance is still fairly well here. It's 92%. And again, when we put all our supermodel, we drop to 89. None of the devices that we have gives you 89 or a 0.89 as a performance that we have. Now, there is a lot more work to do. We need to go beyond the abdominal surgeries. As I said, we have patients going spine surgery, limb amputations, hemipelvectomies that also are a significant, or patients had a lot of hypotension. And also we need to test what happened beyond the first intraoperative event. All the work that I show you is the first intraoperative event. What happened is, is this model performed the same with patients that have multiple times hypotension? And this is hopefully work that is going to happen if we get money from the NIH. And with that, thank you so much.
Thank you, Dr. Cata. Any questions from audience? I do have then one question, Dr. Cata. Did you do it like within MD Anderson settings?
Yeah.
So for your patients, how you guys proceed to basically either commercialize it or go through FDA approval? Any ideas? I'm from UTMB and I work with trauma surgery a lot. We try to solve very similar problems. So would be interested to hear your experience on it.
Well, and Jeff here can help us. So we first of all, we are working with the MD Anderson walls because we believe that we have a unique population of patients. Trauma patients are a whole different sort of animal. That's the very first thing. Second is if we get money, we're collaborating with outside another large institution to validate to do sort of an external validation with another main cancer center in the United States. Going to commercialization. Yes, it's in our intermediate long-term goal, I would say, Jeff. But I think that we are still not there to think on commercialization. I think that there are a lot of more surgeries that we need to test. If this holds true, which I believe is good, then I'm positive about it.
Thank you very much for that.